Ever wondered how scientists can pick out a single particle moving at an exact speed from a beam containing millions? It sounds like magic, but it's pure physics, and the device they use is called a Velocity Selector. Let's break down how this incredible gadget works. Picture this. We have a region with both an electric field and a magnetic field. We'll set them up so they are perpendicular to each other. Now, we shoot a beam of charged particles, like electrons or ions, into this region. The key is that the particle's initial velocity is also perpendicular to both the electric and magnetic fields. So, what happens when a charged particle, let's say with a positive charge Q, enters this area? First, the electric field, which will point downwards, exerts an electric force on it. Since it's a positive charge, this force will also point downwards. The magnitude of this force is simply the charge Q times the electric field strength E. At the same time, the magnetic field, which we'll imagine pointing into the screen, also exerts a force, This is the Lorentz force. Using the right-hand rule, with our fingers pointing in the direction of the velocity and curling them towards the magnetic field, our thumb points upwards. So, the magnetic force acts in the opposite direction to the electric force. The magnitude of this magnetic force is the charge Q times the particle S velocity, V times the magnetic field strength B. Here's where it gets really clever. We have two opposing forces acting on the particle, an electric force pulling it down and a magnetic force pushing it up. Now, think about it. If the magnetic force is stronger, the particle will curve upwards. If the electric force is stronger, it will curve downwards. What if these two forces are perfectly balanced? What if the upward magnetic force is exactly equal to the downward electric force? In that specific case, the net force on the particle is zero. And according to Newton's first law, an object with zero net force acting on it will continue to move in a straight line at a constant velocity. So, for a particle to pass straight through the velocity selector without being deflected, the electric force must equal the magnetic force. Mathematically, that's Q times E equals Q times V times B. Notice that the charge Q appears on both sides of the equation, V. This means we can cancel it out. It's incredible. But the condition for a particle to pass through undeflected doesn't depend on its charge at all. It could be positive, negative, or have a larger or smaller charge magnitude. Doesn't matter. After cancelling Q, we're left with E equals V times B. We can rearrange this simple equation to solve for the velocity V. Find that V equals E divided by V. This is the magic formula. It tells us that only particles with this exact velocity will pass straight through. Any particle moving faster will have a stronger magnetic force and curve up. Any particle moving slower will have a weaker magnetic force and will be pulled down by the electric field, Ds. This is why it's called a velocity selector. By carefully tuning the strengths of the electric and magnetic fields, we can choose precisely which velocity we want to select. It acts like a filter, letting only the particles with the desired speed pass through a small exit slit at the end, while all others are blocked. So, where is this amazing device used? One of its most important applications is in mass spectrometry. A mass spectrometer is a machine that measures the mass-to-charge ratio of ions. Before the ions enter the main analysis part of the spectrometer, they are often passed through a velocity selector. This ensures that all the ions entering the next stage have the exact same initial velocity, which is crucial for getting accurate mass measurements. Velocity selectors are also fundamental in many areas of atomic physics and particle physics research, helping scientists prepare beams of particles with well-defined properties for their experiments. It's a foundational tool that allows for precise control at the subatomic level. So, the next time you hear about particle accelerators or mass spectrometers, you'll know one of the clever little secrets behind them: the elegant and powerful velocity selector. A perfect example of how combining electric and magnetic fields can give us incredible control over the world of tiny particles. Thanks so much for watching. If you found this explanation helpful, please give this video a thumbs up and consider subscribing for more physics content. Let me know in the comments if you have any questions. See you next time.